Hi, and welcome to this video on Simio input parameters. In this video, we're going to learn how we can use Simio input parameters to specify the inputs of our simulation model, and we will also talk about some considerations about when it is appropriate to use this feature. So here you can see a simplified version of the general simulation modeling and analysis process, where we have a simulation model that is a computerized model of an actual system under investigation, say a restaurant, and our model has some input parameters. These inputs can be the inter-arrival times of customers into the restaurant or the service time at the cashier for customers to place their order. And also we have some outputs, such as time in system, number in queue, utilization, etc. And here you can see the main steps of a simulation project. We have input analysis and modeling, where we try to collect data from the real system, analyze them, and come up with models, in most cases probability distributions, so that we can generate similar patterns in our computerized model. We have model development and verification and validation analysis, where we try to make sure that our model corresponds to the actual system and it's correctly implemented. And finally, we run our experiments and we perform output analysis. We compare different alternatives, and finally we make a decision. Note that there are feedback loops between these different steps. So for instance, after you run some initial experiments, you may identify some problems in your model, so you may want to go back, change your model, and perform verification and validation analysis. Also, based on the results of your verification and validation analysis, you may decide to update some of your input models. Now, this video pertains to the input analysis and modeling step. So the general input analysis and modeling process can be summarized as follows. The first step is, of course, data collection or data acquisition. Once we have the data, we need to assess whether the data are independently and identically distributed. This is because most of the statistical analysis that we perform on the data is based on the assumption that the data are IID. The next step is to hypothesize the distribution family that represents the data well. We usually perform some qualitative assessment. So for instance, if we're modeling processing times of parts on a machine in a manufacturing system and the data seem to follow a normal distribution, we may want to reconsider our choice of the distribution, because when you use a normal distribution, it is possible that you get negative processing times, which in this context does not make any sense. As another example, suppose we would like to use simulation to decide how many tables of different sizes we need for a restaurant that we're modeling. So in this case, an input that we're interested in is this group size for people who come to this restaurant. So it would make more sense to use a discrete probability distribution as opposed to a continuous probability distribution to model this input of our model. Alternatively, we can use a continuous probability distribution, but then we will have to figure out a way to transform the sampled values to integer values. We may also visually assess our data by looking at the histogram of the data. We know the histogram provides an approximation of the shape of the distribution that the data is coming from. Once we hypothesize appropriate distribution families, we need to estimate the parameters of these distributions. So for instance, if you hypothesize that the normal distribution is a good option, then you need to estimate the parameters of the normal distribution, which are the mean and the standard deviation. Finally, once we have our distributions and their corresponding parameters, then we need to assess the fit of the distribution to the data. So we use different kinds of statistical tools, such as the goodness of fit test. We can also use quantile or QQ plots and percentile or PP plots to see how well the distribution fits our data. Note that in certain situations, as we will see shortly in this video, we may decide to use the collected data directly in our simulation model. So in those cases, the input analysis and modeling process is going to look different because there is no distribution fitting anymore. So if you're not familiar with the general input analysis and modeling process, I would suggest that you check out our other video modules on this topic. So once we have our input models, we need to specify them in the simulation model. Now in Simio, there are multiple ways of specifying input data. The first and perhaps the most common way of doing this is by putting an expression directly in the object instance properties. So for instance, in the single server model that I have here, I have random arrivals, and my inter-arrival times are exponentially distributed with a mean of 0.25 minutes. Similarly, for my server, I have random.triangular 0.1, 0.2, 0.3 minutes for processing times. There are other ways of specifying input data in Simio. For instance, we can use referenced properties. That's when you define the expression in the reference property, and then you go back to the object instance and refer to that reference property. Another way of specifying input data is by using tables. So for example, you may have an arrival table that specifies exactly what time entities are created in your model. This is used, for example, when you want to replicate a particular situation that happened in the real system. There are also sequence tables that can be used to not only specify the sequence that parts go through, but also the processing times at each step. You may also use a rate table, especially when you have a non-stationary arrival process. We can also use timers and events. So we can specify an expression in a timer element, and then whenever this timer goes off, an event is triggered and something happens in your model. We may also use events that occur in the model. For example, consider a conwip queuing model where you want to maintain a constant amount of work in progress. So every time a part leaves the system, you want to create a new part. So the event of interest here is when an entity leaves the system. And whenever that event happens, you trigger an arrival into your system. So we're not going to go into the details of these items here. What I'm going to do is just go to Simio and show you where some of these can be specified. So I'm going to drag a source object instance here, and if you go to its properties, you will see that for the arrival mode, currently I have inter-arrival time, and I have the expression directly in my source object properties. Now, if I open up this drop-down list, you'll see that I also have the option to use a time-varying arrival table. That's for modeling non-stationary arrival processes. Or I can have on-event arrivals using an event, and this event may be created by a timer or whenever an event happens in the model. Or I can use an arrival table to specify the exact arrival times. While these methods are discussed in detail in other video modules, in this video we're going to talk about an alternative way of specifying input data using Simio input parameters. We can specify input parameters under the Data tab. So in this particular example, I have defined input parameters for my model. So I have my model selected, I go to the Data tab, and click on Input Parameters. And as you can see, we have three different types of input parameters: distribution, table value, and expression. And we'll talk about each type in detail in this video. But before we do that, let's talk about why we use input parameters in the first place. So there are three main reasons. First of all, if we would like to use the observed real-world data directly in the simulation model, in other words, if we want to sample from the actual data that we have collected, in that case, we need to use input parameters. Also, using input parameters allows us to perform two kinds of analysis. The response sensitivity analysis gives us an estimate of how sensitive the outputs of our simulation model are with respect to the different input parameters. On the other hand, the sample size error analysis helps us evaluate the input uncertainty and allocate our data collection resources more wisely to different inputs in our model. Response sensitivity analysis and sample size error analysis are covered in detail in two related videos. In this video, we're only going to focus on how to specify input parameters, and then we'll also discuss the situations where using input parameters may or may not be appropriate. So we're going to use a simple model of an airport security checkpoint to show how we can specify input parameters in Simio. In this model, passengers first visit the dock check station where security officers check their boarding pass and identification document, and then they visit either of the two scanning stations. The AIT station, or Advanced Imaging Technology station, is for regular passengers, while the other scanning station is what we call pre-check here in the US. And this is for passengers who have already gone through some background checks. And the difference between the two is that the pre-check passengers will get to keep their shoes and belts on. There may be some other differences as well, but the net effect is that the pre-check station usually has a shorter line and faster processing time. Now, those regular passengers that go through the AIT either pass and leave the system, or if they fail, not only they need to go through the scanner again, but they will also need to go through the pat-down station. And this is where an officer performs a body search on these passengers. Now, in this model, all of the routings are implemented using the selection weight property of the links. So for instance, 80% of my passengers are regular passengers and 20% are pre-check passengers. Similarly, for the outcome of the AIT station, if a passenger fails the AIT, that means they are screened twice. They go through the pat-down station. If a passenger is only screened once, they fail with a probability of 10%, or they pass with a probability of 90%. Now, I'm using a combination of conditional and probabilistic routing on these three links. And if you want to learn more about how the routing logic works in this model, I would encourage you to watch the related video module in the entity routing video series. Also in this model, we are directly putting the expressions for the processing times and inter-arrival times in the objects themselves. So for instance, for my source, I have the inter-arrival time expression, random.exponential 1/72 hours. Now this means that on average, I have 72 passengers per hour that arrive at this security checkpoint. Similarly, for my dock check, I have random, triangular, 0.9, 1.8, 2.7, and the units are in minutes. Also for AIT, again, I'm putting the expression for processing times directly in the station. Same for pre-check and pat-down. And of course, our main assumption here is that we have already performed input modeling and analysis to estimate these distributions. Now let's go ahead and specify input parameters. Specifying input parameters in Simio is fairly straightforward, and it consists of two main steps. First, you need to define the input parameter, and in the second step, you need to tell your object instance to use that input parameter. So let's start with our inter-arrival times. Now, in order to define my input parameter for inter-arrival times, I need to go to the Data tab and then click Input Parameters. And now, as you can see, I have three options. There are three types of input parameters, as we mentioned earlier: distribution, table value, and expression. Now, for my inter-arrival times, I'm going to use an expression input parameter. So the first thing I'm going to do, I'm going to rename it to inter-arrival times. And as you can see, here I can specify the unit type. I'm going to leave it as unspecified. And the only thing I need to do is just define the expression here. Now, when you use an expression input parameter, it allows you to perform response sensitivity analysis, as we will talk about in a related video, but you cannot perform the sample size error analysis because you don't tell Simio based on what sample you came up with this distribution. So I'm going to go back to my facility view and simply select my source object, copy this expression, go back to my input parameter, and paste it. So I'm done with the first step, which is defining the input parameter. Now I need to go back to my source and tell my source object to use that input parameter. I'm going to go to inter-arrival time, open the expression builder, and I'm going to select inter-arrival times, which is my input parameter. Say OK. So now, instead of using the expression directly here, I'm referring my source object to the input parameter to determine inter-arrival times. So now I can run the model just to make sure that I don't get any errors. Next, I'm going to define an input parameter for my doc check station. So right now, for the processing time of the document check station, I have a triangular distribution with a minimum of 0.9, a maximum of 2.7, and a mode of 1.8 minutes. But this time what I would like to do is I would like to directly use the observed data that have been collected in the simulation model. So here I have an Excel worksheet that includes these observations. So I have my doc check times that have been collected from the real system. And if I select all of them, you can see that I have a sample of size 350 observations. Now, in order to directly use this sample in the simulation model, we need to define an input parameter of type table value. So I'm going to select table value. I'm going to rename it to doc check proc times, document check processing times. And as soon as you define the table value, you see that you have an error in your model, which says, well, for this input parameter, for the table column property, you have an invalid input. And you can see the pink box here that shows you that this is where the error has occurred. So here I need to define a reference to a table column, but I don't have a table yet. So what I need to do is go to tables and define a new data table. I'm going to call this doc check table. And what I need is a column to store these observations. So I'm going to use a column of type, a property of type real. So I'm going to change this to doc check observations. And what I can do is go back to my Excel worksheet and simply copy my observations and paste them in Simio. So now I have my observations stored in this table. Now I can go back to my input parameter, docCheckProcTimes, and tell Simio to use that column in the docCheck table. And what Simio does, it generates a histogram based on a sample of size 10,000 drawn from this table. Now, the way Simio samples values from this table, either for generating this histogram or during the simulation run, is that it samples values based on their frequency. So if I have value x that occurs twice in my sample versus value y that occurs only once, then when Simio is sampling from this table, the probability that x is sampled is twice the probability of y being sampled. But for now, I'm just going to assume that I have determined that using the observations directly in my simulation model is an appropriate way of modeling this input parameter. We'll talk about the things that you need to consider when deciding whether or not to use observed data from the real world directly in your model at the end of the video. Also note that when you use an input parameter of type table value, you can include this input parameter not only in the response sensitivity analysis, but also in the sample size error analysis. Because now Simio knows the sample size that you use for this input parameter in your model. And of course, if you don't want to include this input parameter in any of these analyses, you can change the value to false. Finally, the random stream property of a table value input parameter simply specifies the random stream number that will be used by Simio during the simulation run when sampling from the values in the table. So now that I have defined my input parameter, the next step is to go back to the facility view, select my docCheck station, and tell Simio to use this input parameter instead of this expression. So I'm going to open the expression builder, and what I'm looking for is my input parameter. So I see docCheck, docCheckProcTimes, docCheck table. If you forgot what name you use for your input parameter, the symbols here can help you figure out which one is your input parameter. So when I see this histogram symbol, I know that this is my input parameter, so I can say OK, and I can run the model real quick to see if I see any issues. Next, we're going to define an input parameter for our AIT server. So right now, for the processing time for this server, I have a triangular distribution with a minimum of 1.2, maximum of 3.6, and a mode of 2.4 minutes. And what I'm going to do now is, again, use a table value input parameter for this server. So I have input parameters selected here, and I'm going to define a new table value input parameter. And again, I immediately get this error message that says, well, for the table column property, you don't have a valid reference. So what I'm going to do is rename this to AIT proc times, AIT processing times. And now I need to define my table. So I go back to tables and I define a new table. I'm going to call it AIT table. And again, what I need is a standard property of type real. So what I'm going to do is rename this to AIT times. And now I can go back to my Excel worksheet, and you can see I have another worksheet here that contains my observations of processing times for AIT from the real system. So if I select all of them, you can see that I have 275 observations for this input parameter. So of course, again, just like what we did for docCheck, I can copy and paste these values in my table. This time I'm going to do things a little bit differently. I'm going to bind my table to my Excel worksheet so that if I end up collecting more observations, say as a result of running the sample size error analysis, I can simply record my observations in my Excel worksheet and simply import the updated sample into Simio. So I'm going to bind my table to an Excel worksheet. So I've saved this file on desktop. This is my file, observed data. So I'm going to open this, and then Simio is going to find the worksheets in that workbook. And I have two worksheets, dog check values and AIT values, which is the one that I would like to use here. You can also specify the range for your worksheet. For now, I'm going to use the entire worksheet. So say OK. Now my table is bound to Excel, and I can simply import the values. So I can just go to import, say import, and voila. I have all my observations, all my 275 observations imported into Simio. So now I can go back to my input parameter and fix this issue. I'm going to select my AIT table dot the AIT times column. And again, Simio generates the histogram. And you can go back to the facility view, and simply for the processing time expression, I'm going to select my AIT proc times input parameter. Say OK, run the model. So the next station I'm going to look at is the pat down station. And right now what I have for the processing time expression is random.triangular 5, 10, and 15, and the units are in minutes. So what I'm going to do is go to the Data tab, Input Parameters. I'm going to define a new input parameter, and this time I'm going to use distribution. And I'm going to change its name to pat down proc times, pat down processing times. And as you can see, the default parameters are as follows. The distribution type is normal, the mean is 1, and the standard deviation is also 1. So when Simio generates the histogram, I see a histogram that looks like a normal distribution. So for this input parameter, we're going to use the triangular distribution family, and our minimum is 5, mode is 10, and the maximum is 15. Now there are two other parameters that we can set here. We have the random stream number that Simio uses to generate this histogram, and also to generate observations during the simulation run. There is another property here that is the number of data samples. When this property is set to 0, as you can see, we are able to include this input parameter in the response sensitivity analysis, but since Simio doesn't know the sample size, you cannot use this input parameter in the sample size error analysis. However, if I tell Simio, for example, that this distribution is based on my analysis of 35 data points that I collected from this process in the real world, then Simio allows me to decide whether or not I want to include this in the sample size error analysis. So basically here I'm telling Simio that based on the 35 observations that I've collected, I performed input modeling and analysis, goodness of fit test, and all those steps that we talked about at the beginning of this video. And I've determined that this distribution provides a good fit for the sample that I collected. So now I can go back to the facility view and tell my pat down server to use the pat down input parameter. Finally, the last station that we're going to look at is the pre-check server. And for this server, what I'm going to do is simply use an expression input parameter. So I'm just going to copy this expression that I have for the processing time, go to the Data tab, Input Parameters, and define a new expression input parameter. I'm going to change its name to pre-check times, and paste the expression here. So now I'm going to go back to my pre-check server, and instead of putting the expression directly here, I'm going to say use the pre-check times input parameter. Now, in order to verify that our model with input parameters corresponds to the model that we started with, what I have here is the initial model and the model with input parameters on the right, and I've performed an experiment with 50 replications using the two models. And what I'm going to do is simply compare these values of average time in system, average number in system, the utilization of the stations, and so on, as a way of verifying that we have implemented the input parameters correctly. You can also compare the SMOR plots for the different responses that you've defined, just to make sure that everything is working properly. And of course, the differences that we see is mostly due to the fact that for some of these stations, we are sampling from the observed real-world data, which may not cover the entire range or may have gaps in them. But visually, by looking at these results, now I have more confidence that I have implemented the input parameters correctly. In the last part of this video, we're going to briefly discuss some of the important things that you need to keep in mind when deciding whether or not you should use real-world data directly in your simulation model, like what we did using table value input parameters for our dock check and AIT stations in our airport security checkpoint model. The first thing that we need to consider is sample size. So generally we want larger sample sizes when we directly use the real-world data collected from the actual system. And this is mainly because we typically run very long simulation runs and also many independent replications, which means we're simply going to run out of observations as we're sampling from the actual collected data. For instance, if I run my airport security checkpoint model for 365 days and I perform 100 replications in my experiment, I probably sample thousands, if not tens of thousands, observations from my data tables. I'm just sampling from those 275, 350 values only. The other thing that we need to consider is coverage, which is kind of related to sample size as well, because as the sample size increases, we expect to have better coverage. But there are some other things that we need to keep in mind as well. For instance, we need to make sure that our data represents the range properly. Suppose that you're collecting data from a manufacturing process, and this manufacturing system uses raw material from two different suppliers, supplier 1 and supplier 2. Now suppose that during the time that you were collecting data, they were using raw material from supplier 2. And as you can see here, if you had observed processing times when they were using raw material from supplier 1, then you would have had more variation in your processing time. As you can see, the range is different for these two suppliers. The other thing that we need to consider is extreme and infrequent values. Now, this histogram here is based on thousands of replications from an exponential distribution. And I had to collect so many observations so that I can get just a few observations of these extreme values that are way at the end of the tail of the distribution. Now, if you collect data from a real system, you may not be able to collect so many observations. So there is a chance that you do not have any observation from these extreme points, which means when you sample from those data that you've collected, you're never going to sample a large value like these here, which may have a significant effect on the results of your simulation experiments. The other thing is gaps. For example, suppose you have a large sample and a small sample, and as you can see in the small sample, there are some gaps in my observations. I don't have observations of some intervals that can happen in reality. Again, keep in mind that when you're sampling from the data that you've collected, you're stuck with those data points. You're never going to get a different value than the ones that you've already collected. And of course, this smaller sample is also missing the extreme values and infrequent values that we talked about earlier. Now, the question is, how much do we care about the tails of the distribution in our analysis? In general, for queuing models, for queuing systems, these large values at the tails of the distribution can have a significant effect on the congestion of the system. So time in system, number in system, their percentiles can be affected significantly if you do not consider these extreme points in your input models. And finally, sometimes you may not be able to find a reasonable distribution that fits the data well. Given that there are hundreds of distributions, and some of these distributions, like the beta distribution, are very flexible in terms of the different shapes they can take, it's unlikely that you cannot find any distribution that fits your data. However, a more plausible scenario is when you're using a statistical software that only tests the fit for a limited number of distributions. And it turns out that none of those distributions that your software supports is a good fit for the data that you have. So in this case, you may want to decide to use the real-world data directly in your model, considering the things that we already talked about. The other scenario that distribution fitting may fail is when you have too much data. And what happens is that the statistical power of any goodness of fit test will be so high that even minute deviations from the hypothesized distribution would result in a rejection of the null hypothesis, which means that even if you have a distribution that visually seems to provide a good fit for your data, your goodness of fit test still rejects that distribution. So this concludes our video on specifying input parameters in Simio. As I mentioned earlier, input parameters also allow us to perform two kinds of analysis: the response sensitivity analysis and sample size error analysis. And these are the topics of two related videos that I would suggest you watch to be able to fully appreciate the value of using input parameters in your simulation models.